Continuing our journey into tractability, you'll recall that we've been looking at the limits of computing and algorithm performance, and we're using the traveling salesman problem and using the brute force algorithm to illustrate this. And in the last session we found that if we were trying to find the optimal route by brute force, I find all the routes then pick the best one, then as the number of cities increased, then the number of routes to check increased as a factorial, not exactly as a factorial. So instead of, if the number of cities is n, it's not n factorial, it's actually n minus 1 factorial and then divide by 2, because there's routes both ways. But we're going to see that that's actually irrelevant. So we are going to look at the computer science field guide to see what the problem is. So the computer science field guide, easy enough to find on the internet, the topic of tractability. There's heaps and heaps to read about. It'd be great background reading. But specifically what I want to look at is this algorithm timer thing down here. It's quite a useful, very useful for this particular topic. So what this does is you can set the number of things you check per second. So in our case, it's going to be the number of cities, number of routes that we're checking per second. We can set the number of processes as well. We can set the number of cities. So for example, if we have 10 cities and we have an algorithm that goes up as a n squared, and then it's going to take 100 seconds. So that's no bother. Now, if we were to say take that 5 cities and do it as a factorial, that's the 120. We saw that before. And if we change it to 6 cities, 720 seconds. So let's just think about this. If we're doing 1 operation per second, 720 seconds, that's, how long does that take? Change that to minutes, 12 minutes. That's a bit long. I don't like waiting 12 minutes for a computer to finish what it's doing. But that is not, no computer ever made has been that slow, I don't think. So we can up the number of operations per second. So if we say make it 100 operations per second, then 7 seconds, I can live with 7 seconds, not too bad. Now we're going to go up, I'm going to jump up a little bit and say let's go with 10 cities. Now I am being a little bit inaccurate. You remember that whole n minus 1 factorial divided by 2. Let's not care about that, because we're seeing straight away that going to 10 cities from 6 cities, that's quite a lot of seconds. That's actually like 10 hours. That's not okay. But again, this is a very slow computer. Again, I doubt there's ever been a computer quite so slow that it only does 100 operations per second. So let's say 10,000 operations per second, and we're into, what was that, about 6 minutes? That's not great. Can we go bigger than that? 100,000 operations per second, and yeah, 36 seconds. Not great, it'll do. But let's just think about this. That's just going from 6 cities to 10 cities. That's not a lot of cities. Let's jump up again. Let's go to 15 cities. And you can see straight away, even keeping this 100,000 operations per second, we've gone up to, what are we talking here? Ooh, 151 days. That's really not okay. Let's bump the number of operations per second up. So 1 million operations per second. Ooh, that's still quite a big number. Oops, we're not allowed to go that many. So we can only go up to 1 million operations per second. But luckily these days our computers have loads of processors. So if we go 10 processors, 1.5 days, that's not great. Or 1,000 processors, that'll do. All right, 1,000 processors, we're down to something we can live with, aren't we? 21 minutes, not brilliant. Given how things have been going, I'm going to live with it. And that was going from 10 cities to 15 cities. Let's do that jump of 5 again. And we'll go up to 20 this time. Ay. Caramba. What are we into here? 77 years. I think we're going to need some more processors. Let's throw some more processors at this. Oh, we can't. We've hit the limits of what they'll let us do here. But you could see straight away that doing the same size jump from 10 to 15 and then from 15 to 20 led to quite different results. We could cope with the 10 to 15, but the 15 to 20 we could not cope with. And that's what factorials do to us. I'm just going to talk a little bit further. So if I was to go from 20 to 21, I'm multiplying by 21. And then if I go to 22, so going from 20 to 22, I first multiplied by 21 and then I multiplied by 22, which means I actually multiplied by 400. And if I went to 23, 400-ish, I should say, and multiplied by 23, so going from 20 to 23, that's times 21 times 22 times 23. So that's effectively multiplying by 8,000. And that's just going from 20 to 23. So this is the key issue with tractability. It's not that there's big numbers of cities or anything like that. The key problem is that small increases in the number of items lead to unmanageable increases in the amount of computing resources needed. So imagine, and we could go there if we said we've managed to find a situation where for 100 cities, which is a really big number to deal with, we had bought all the computers in the world, set up all the data centers. We were able to solve that in like a couple of minutes for 100 cities. All a person would need to do at that point is say, oh, we're not doing 100, we're actually doing 102. If you think about that, that's 100 times 101 times 102. So that's times 10,000. So now, no matter how many resources you've managed to pull together, you've now got to get 10,000 times more than that to get the problem solved in the same time. So that uncontrollable growth, I'm not going to use the word exponential, but that uncontrollable growth is the key issue that we are dealing with tractability. So I hope that's made a bit of sense. And clearly this is a disaster, and we need to think now about what can we do? This poor traveling salesman, how is he going to cope? So that's next time.